All right, let's get going. Boy, there's a lot of people here today. Guess it's review day. So I hope you guys enjoyed your weekend. I think I mentioned I was in Seattle all weekend. I got off a plane about 4 hours ago. There happened to be a medical emergency, actually 2 medical emergencies on the plane ride out on Friday, which was a little scary. We did end up landing, but I'm actually not sure one of the people made it. But I know, kind of crazy. But I'll tell you that story some other time, not on tape. Anyway, so here's what we're going to talk about today. We're going to do a review for the midterm, which is Wednesday. Okay? If for some reason you are not going to be able to take the midterm either during the morning session or the afternoon session, you have to tell me about that beforehand, and we have to work something out. I generally do not like to give midterms early, just because that kind of compromises the security of the exam. Later, there's also a security issue. What I'll probably end up doing is making a similar but possibly harder exam for later. But anyway, we'll work that out if you do have questions. But please don't just skip the exam and expect to like say, oh, I missed it. Sorry, when can I take it? Not going to happen. You got to email me prior to that. OK. A couple things today. We'll do the UNIX tip of the day. I have a couple comments. I completely forgot to mention this last week, and I apologize, about TAs and office hours and so forth. And then we'll do the midterm review, which I think should be hopefully illuminating. We'll kind of go over everything I expect you guys to know in a broad spectrum, and then we will talk about some specific types of questions you'll be able to see. Before I do the UNIX tip of the day, comments on TAs. So I got a piece of anonymous feedback last week which disturbed me in that it was, all it said was, I wish TAs would show up for their allotted times. I was here at the lab and there were supposed to be TAs here and there weren't any. So we do not like it when that happens. If that happens, you can certainly use the anonymous feedback, but I would just as soon you just like email me with the name of the person that's supposed to be there. There could be a few things that's actually happening here. The TA could have skipped the lab or whatever and not posted something on Piazza. Bad news. The TA could have been in some other lab in the area and just not been, like, you couldn't find the TA. That's also bad because the TAs should be circulating around and should have their name up and so forth. Or it could have just been, some other kind of fluke where the TA was there, you didn't see him, whatever. But if you find that there's a TA not there, look, we're paying the TAs, so they're not doing this kind of like on their own, right? This is like a job. And Bruce and I have talked to that TA in particular who did miss that time and made it very clear that that's not going to happen again. So they are there for your benefit, and I do not want like you guys to go to lab and somebody not being there. That's like really important to me. So please let me know as soon as you can if there are particular people. And if you know a name, great. I mean, if you don't know a name and you don't want to give up a name, fine. Do it anonymously. We'll track the person down. It wasn't that hard to figure out who it was. So I just wanted to comment on that. I did not ignore that email from the person who anonymously posted it, but I couldn't actually email you back because you didn't give me a way to do that. So anyway, I wanted to let you know that we took care of the problem. It should not happen again, but if it does, please email me. That's like bad news if TAs aren't showing up. OK. Let's see. The UNIX tip of the day. So let's say it's Tuesday night and you're studying, but you're like, I don't understand this stuff. And maybe Chris put a little midterm exam online, like on his page, and I want to find it, right? And you go, how do I go and look through directories? Well, there's a find command. Now, luckily, I actually have permissions on my directories that I doubt you'll be able to actually see this. But let's just say you wanted to find a file in your own folder, right? And let's say it had, it was named something along the lines of midterm. If you do find -i name, which means find by name of a file, and don't worry about the case. In other words, I could call it midterm or like with uppercase and lowercase or whatever. And then you type in quotes midterm star, which means anything, or you could even type star midterm star, whatever. That would find everything that had the word midterm in it, right? And you'll find out that, oh look, Chris did do that, right? And like there's the midterm thing, right? And then you can go and you could maybe list it out, right? 2014 midterm, and it finds both the folder and the thing, right? And then, of course, I say, you're not going to get the thing, right? But But if you want to find your own files, especially when you get lots and lots of files in your directory, the find command is kind of cool. You can do it with find. What you do is you do find and then the directory you're looking for. I forgot to mention that. The directory you're looking for, generally, dot, which is like the current directory you're in. Or you could do slash, which would try to look through everybody's folder. And it would give you lots of, I can't look at that folder because the permissions are set wrong. But you could do that. Dot would go from the current command you're in, dash name or iname, and then the file name in quotes. Or you could do like type equals, I forget what it is now, type equals file, I believe. And then midterm, star. And that, nope, hang on, man, find. Let's see. Remember, you can always look through the manual to find what it is. Hang on. Or you could just ask Bruce, who knows these things. Hang on. Type. There we go. Type dash type, and then just the type F being a file, D being a directory. If you want to look for a directory, you can do it that way. So lots of different options on here. So if I wanted to find type that's a file, like that would just, nope. Type F maybe? No, I'm still doing it wrong. Hang on.
So you need to have the iname and the midterm.
That's right. There we go. Dash iname. You have to do it in the right order. There we go. So anyway, so you can use that command. But it is helpful if you're saying, where did I put those files? They're in my directory somewhere. Oh, I can find them. OK? Relatively straightforward. Questions on that? OK. All right, let's jump into the review. So the midterm is Wednesday during class. If you can't make the morning one for some reason, if you have some other obligation, then come to the afternoon one. Again, email me if there's going to be some reason you're not going to be there, because it's a 0 if you just don't show up and I don't know about it. Here's some general study tips. OK, 1 page, back and front, handwritten notes. I've already mentioned that before. Review all the slides. I mean, I put the slides together. Again, I try not to kill you guys with PowerPoint too much. And if I am, please send me an email and say, too much PowerPoint. We need more like stuff on the board or whatever. I don't want you to, I don't want to sit here and read all the slides, right? But they're there so that you can go and see what some of the things that we talked about are. You can obviously go back and look at all the videos. That would take a long time. But you could look at the videos, especially if you missed a class and didn't look at the video the first time. Go watch that video, right? I put notes online, or I put some notes online that aren't slides, not too many times. I put code samples. Look through the code samples. Okay? If you have questions about those, put something on Piazza. All right. Homework assignments. Okay? There will be questions that are about the day class and the event class. Now, you should not need to know details. I will give you enough background information in the test question so you don't have to go, what was the name of that variable? Right? You're gonna have that in the exam. But you should know kind of what the idea was about inserting or scheduling events and so forth. I just want you to be able to talk about that, because that gives us a framework to start with that we can add a little bit onto. Okay? And then finally, review the labs. I mean, we did a bunch of labs in here, and those kinds of questions from the labs, like, hey, in the maze search, what did we, what kind of search was that, et cetera, that sort of thing. So just go back and review all that stuff. And that in itself can take a while, but I think you'll get some benefits out of that. Questions on that? OK. The types of problems we're going to have. I'm going to have some short answer stuff, like a lot of, not a lot, but a fair amount of the test will be things like, explain why this is the case. Like explain why this algorithm is order n squared, right? I'll give you some double loop, and you'll have to explain why the algorithm is n squared. And I just want a sentence or two to answer the question. There's also going to be some find the bugs and actually fix the bugs type questions, right? Like, here's some code. Something's wrong with it. What's wrong with it? I will not be testing you on C++ syntax on those kind of questions. It will be logic kind of issues generally. Okay? You won't have to look and go, oh, he missed a semicolon here. No, that's not what I'm talking about, right? I'm talking about you set the variable I to one more. You went too far through the variable or something logic-wise. Make sense? Okay. But you will have to do a little bit of explaining C++. So we talked about those big things that a few big things, like the big three: destructors, copy constructors, operator equals sorts of things. We also talked about a reference variable versus a pointer. I will not make you go into too much detail in that, but kind of the broad overview might be important. Okay. So those are kind of general tips on overall the big picture here. Questions on the big picture? No? OK. Well, here's the topics we covered so far. None of them should be too, like you should recognize all those. If you don't, you missed a class, I'm guessing, or fell asleep during a class. The stuff at, you've seen lots and lots of this, right? We've seen a fair amount of this. We did a couple things on stacks and queues, trees. We did lots of stuff on trees. This is not to say that like this whole amount will be about trees, but we happen to go into a bunch of different things on trees and tries and so forth, and priority queues and all that. Okay? You should be able to talk about any one of those. If I said, what's a stack? You'll be able to say, oh, look, a stack is a first in, last out structure, and it has pop, and it has push, and it has top, and so on and so forth. Okay? You should be able to discuss all the ones we talked about. Priority queues, I mean, that was like the last thing we did. I don't expect you to know that many details about it. But you should be able to say things like, OK, a priority queue has keys, and it has values, and you're going to prioritize this structure by the key, and you can only find the minimum, that sort of thing. OK? Basic stuff like that. All right? These are all online, these slides. OK. So let's go through some of these individually. In fact, we'll just kind of walk through the list, and I'll give you the highlights. OK? It's like fast forwarding on the videos. I talked about this already. Destructors, copy constructors, operator equals overload. What's a reference type? Right? Dynamic versus automatic memory. Like, a lot of people are still a little bit confused about what happens when you use the new operator versus when you use when you just use the constructor and you set a variable equal to some. You set a variable and you say day. Here, I'll write it down, like the following. It's always a little scary when you forget to look under the back and you're like putting this up. You're like, oh, what's going to be back there? All right. So remember, when you do something like day, right? D equals, well, day D, something like that, right? That is going to call the constructor on D, and that is going to do what kind of memory? Is it going to be dynamic or automatic memory for this? It's going to be automatic, which means at the end of whatever function this is in, this guy goes away, right? So you've got to either copy the data out of it or copy or set the data equal to something that is going to stick around, right? Versus if you said day star D equals new day, right? Right? Or an array or something like that. Different idea. This is the automatic memory. So you should be able to talk about that and kind of recognize the differences when we do that. Okay. I might also ask you, look, we've talked a lot about asserts. I might say, hey, when's a good example of time to use assert? You know, when you know that the program code should be doing, you should get input to your program that fits a certain framework, well, then you can use an assert and say, at this point, if this Boolean condition is not true, I have to crash the program, basically. Okay, those are the things we talk about when we do asserts. Is asserting mainly used for debugging or for error finding? Or, you know, I should say error checking during your program? What do you think? If it's for error checking during your program, how many times does Microsoft Word crash and say, assert failed? Right? I think I've seen that like once in my life, right, with a professional program. Right? You try to take these things out when you're making professional programs and actually handle those errors internally. But sometimes you can't handle the errors and you do need to crash the program. So asserting is more for debugging than for actual error handling. But that's digging a little deeper into the weeds. Okay. Questions on C++ stuff? All right. Sample type question I might ask. So explain when a destructor is necessary in a C++ program. When is it OK to use the default destructor? Anybody want to give me an answer to that? We're not going to go over like all the answers to these, but I do want to, if anybody wants. Remember when we need a destructor, like we actually explicitly have to produce a destructor? Maybe I should ask that now. When you what? Yeah, if you use new somewhere, you're going to need a destructor of some sort, or you're going to need to use the delete at some point. So if you use new and then at the end of your program you still got memory or end of when the class gets destroyed in some sense, you're going to need to have the destructor free all that memory, or you get memory leaks. Right? So yeah, if you've got automatic memory, you don't need, if your whole program is made of automatic memory, you don't need any destructors in there explicitly. The compiler will build one for you, and that should work just fine. Okay? That's the type of thing we might ask you for C++. Other questions on that?
What about the next part?
When is it OK to use default destructor? Yeah, when you have automatic memory, you can use the default destructor. In other words, if you don't use new anywhere in your program, right, you're not going to have the compiler will create a destructor that will work just fine for you. And the compiler makes a default destructor until you make one. It puts one in there for you, and it doesn't really do anything. It's actually an empty function because nothing needs to be destroyed. No memory needs to be destroyed that you created. Okay? Or freed, I should say. All right. OK, that was C++. So we also talked a lot about static and dynamic arrays. Right? You need to know the differences between them. You need to know, about why you would use static arrays versus dynamic arrays. What are the downsides to using dynamic arrays, right? You need to have some sort of destructor generally. You need to control that memory. Other downsides, well, you do have to expand them, and that takes some time, right? What's the asymptotic behavior for all of our dynamic and static arrays, right? Generally, we have order n behavior because we have to look through for like moving things. We have order 1 behavior when we're doing just lookups, right? Because you got an index, you go right there, you don't need to look through everything, that sort of thing. Okay. Why are arrays good? Why are arrays? How are arrays laid out in memory, and why is that good? Right? We've talked about that a number of times. The difference between having an array in memory like this, right, where you've got boom, 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 right next to each other in memory is that array, which makes it nice. You can walk through it, and it's in one block of memory, versus a linked list, which could, if this was the memory system, a linked list, this one could point over to here, and this one could point to here, and this one could point back over to here, and then this one could point to some other place in memory over here, and not contiguous in memory. I need to know about that sort of behavior. Okay? I'm not going to go into details about all this stuff because those are what the other labs were. That's what the other stuff was for. Questions on it, though? OK, you want to see a sample question? Write the insert at index function for an array. So I'll give you kind of a framework, and I'll say, here, I want you to write the little function that is insert at index, right? And it would have like index int I or something in there, or n or whatever, right? And I'll tell you what the function does. It'll insert a value at a particular index and move all the values above the index to the right by 1. Pretty standard stuff. Okay? Make sure you know how to code these to the extent possible that you can. Yeah.
So for this one, would we have to worry about any?
For this one, I would probably say in here, you do not need to worry about expanding. Just write the 3-line function that takes the index, plops it into the right, finds which one it needs to be in. I would say, hey, or it doesn't even need to find it. You've got the index. Go to that index, move everything right one, plop it in there. Yeah, you wouldn't have to. I would be explicit about that. Now, I mean, I could say, write the expand function or something like that too, but that wouldn't be part of this particular one. Good. All right. OK. Then we talked about linked lists. A number of things about linked lists. We did a bunch of labs on them. We did the homework assignment on it, homework 2. Right? Linked lists, of course, have nodes. You can either make the node out of a whole class or make it a struct for just the node. The whole point about that is that they are self-referencing. Right? You've got a node. Inside that definition of a node, it points to another node. And that's the whole idea of a linked list. right? It links to other nodes that aren't next to it in memory, right? You have to walk through the list to get to values generally, which can take time, which means we have to worry about asymptotic notation about linked lists. A lot of times they're order n because you have to walk through things. If you're clever, you'll keep a pointer to like the head or the tail. In fact, you kind of always have to keep a pointer to the head, right? And you need to worry about all those special cases about handling the head. If you're going to insert into an array or a linked list and you insert at the beginning, remember the head needs to now point to the new one, not the one that it already pointed to, or you're going to kind of lose that. So you need to know about that. Okay? Be able to reason through linked lists with pictures, right? And be able to say, OK, here's a drawing of a linked list, right? Here's some links like this. And I might say, and this is like the head, right? And I might say something like, or maybe it's a doubly linked list, right? And like that. And I might say, OK, show me how to insert a node at the last node, something like that. And you'd have to draw the picture. And you say, well, I put in a node over here. And then the first step is like that's the first step. And you might talk about it. And then this one needs to point back to here. And this one needs to go to null, et cetera, et cetera. So be able to draw those things. OK, go back and look at your thing. And that's super important for the logic part of these data structures. OK? Any questions on those? That sort of idea? And remember, like deleting a node in a singly linked list, you can't do it unless you have the previous one. Why? Because what happens? How do you, in a singly linked list, if we were to try to delete this one and we only had that one, what would the problem be? The previous one, it would link to nowhere if you deleted this one, and you have to know where this one is. How do you get to this one if it's a singly linked list? Well, you either get it when you get it passed in, which is kind of ugly code-wise, or you go back and you walk down until the next of the one that you're looking for is the one that you're deleting. So there's various ways around that. OK? All right, a sample type question for this. Oh, no, more stuff on it. Sorry. Go to the sample type. Doubly linked lists. Yeah, we talked about that. Deleting only requires a node for a doubly linked list. This is, you guys found this out when you did homework too, right? I think a lot of people said, ooh, I don't really get, or I didn't, a lot of people didn't, the first time through anyway, make the links go properly, right? And do that loop where you're kind of looping through each link. That's a tricky operation, especially when you have the doubly linked lists. And the singly linked ones, you have to keep track of that previous one somehow too. So make sure you review the code from that. And then we also talked a little bit about circular linked lists. In other words, at the end, the tail points back to the head, and then you could walk through forever, right? And I could ask a question that said something like, for a circular linked list, if you want to walk through the whole list, if you're given a node, number one, can you walk through the whole list? Yes. Number two, how do you walk through the whole list without going on forever, right? So you could answer that. Okay. Here we go, sample question. So find the errors in a linked list. Oh, this is like find the bugs in a linked list. This is one where this would be kind of a mean one, I suppose, but it would be, you'd have to look at the list implementation and say, OK, in the insert before, what am I looking for? Right? I might ask insert before some node, tell me if this program will do what it says it will, if this little function will do what it says it will. OK? Be able to answer those. Questions on linked lists? I might go in a little more detail and say, what other linked structures do we have? Well, that's coming up later, right? We have lots of linked structures. They are not all linked lists. Trees are linked structures, not linked lists. In general, they are. Okay. All right, we talked a bunch about recursion. Okay, what do you need to know? You need to know that recursion is not magic. I'm not going to ask you that. Is recursion magic? No, I'm not going to ask you that. But you need to know that recursive functions call themselves, and the compiler takes care of all that stack-like stuff, right? You need to be able to write a simple recursive function. So there's a lot of things that are easily written recursively. I will not ask you for a hard one, right? I will not say, do this weird special case that's going to be. I would not ask you to, for instance, try to shoehorn a level order tree traversal into a recursive function. I'm not even sure it's possible, right? One of the TAs and I talked about that one time, and it might not even be possible. I'm not going to ask you to do that. I mean, if I ask you to write a recursive function, it'll be like 2 lines long or 3 lines long, right? But you got to be able to reason through at least the base case and what's happening in the algorithm and how you can do that recursive function. So reviews recursive functions. Question? No. Okay. Let's see. Lots of different ones. We had lots of different examples. Fibonacci, b to the n, factorial. All those things were there. And I might ask you, so I could say, hey, what's wrong with the Fibonacci sequence in that very pretty but not particularly efficient, in fact, very poorly efficient method? Why is it bad? Right? OK. So here's a sample question. Write a recursive function to calculate the sum of the first n even numbers. I mean, you can say, hey, how are we going to do that? Well, let's see. Anybody want to walk me through the logic here? Sum of the first n even numbers. You do that recursively. Think about it for a minute. Yeah, go ahead, Abby. Would your base case be when you get to the nth even number? Yes. Would it be? It would. That's a good base case, right? If you're counting up, good, awesome. And then so each time, are you going to want to increment n by 1? Probably not. You're going to want to increment it by 2. So you'd have to put those, that in there, right? Let's just do it. Let's see if we can do this right here. OK. All right. So we've got the function, and it's sum evens. All right, we're going to return an int, let's say. Sum evens of int n. Right? OK, so let's see. So Abhi says, OK, the first thing we need to do, if n is what? So the first n, so let's say n was, I don't know, if n was 5, right? If n is what are we going to, how are we going to stop? OK, we can do if n is 0. Yeah, sure. And by the way, if you want to write other cases that do or don't matter, that's fine. If n is 0, what are we going to do? We're going to return what? 0? This might be a harder one. I didn't even actually look through this. This might be a harder one than I think. The one I might ask you would not be hard and too much logic. But OK, return 0. Then what? Are we going to have to count down or up on this one? We're going to have to count down on this one, I bet. Right? So let's see. What's that? Actually, I think this might be a little harder than I thought originally. Oh, well. See if we can figure it out. What do you think? Making you think at 10 a.m. Yeah, go ahead.
If it comes down and we come to 0, then we return 0.
If it comes down to 0, return 0, maybe. Yeah, OK. I mean, well, that's what this is saying, right? Let's just think about this. How would we actually do this, right? Let's say we've got n, and we've got n 0, 1, 2, 3. Let's just work this out. We've got some time. Let's just work this out. If n is 0, what's the sum of the first 0 even numbers? 0. OK. If n is 1, what's the sum of the first 1 even number? 2. How about 2? 6? First 2 even numbers. Well, it depends. If we start at 0, yeah, we got to start at 2 and 4. OK, 3. 12. It's going to be 2 plus 4 plus 6, which is 12. Oh, boy. All right. So OK. So let's see. And then let's make this 3. If we're going to do that, OK. How are we going to set up the first? Let's see. We've got to go count backwards. Yeah, go ahead.
Return n times 2 plus sum within n minus 1.
Oh boy. Return n times 2 plus the sum of n minus 1. Sorry, sum even. Yeah, sum even of n minus 1, like that. Let's see. Would that work? Let's see. So n minus 1, it's not going to matter for 0. It's going to matter for 1. We're going to have n times 2. So the first time through is going to be 2 plus, perfect. Okay, the second time through. N times 2 is going to be, or the first time through if we did 2, it's going to be 4 plus the sum of 2. There you go. Plus 2 gives you 6. That would work. And then 3, same thing. I like it. That's good. That was a 2-liner. I probably wouldn't make it even quite this much like thinking, but that's very good. Okay? So, and you could work it out for or you could walk through the other events. But really, that's kind of a nice, short example of a recursive function. It will not be more than a few lines long. If you're saying, oh no, I need more space, you're probably doing it wrong. Okay? Good. How are recursive functions and stacks similar? Right? You might have to answer that qualitatively and say, what's going on with a recursive function? Oh, it's returning. It's actually storing the state for the function that's doing the calling, and then it stores the next one, and it walks itself backwards as returns come, and that's a first in, last out situation. Okay. Good. Questions on recursion? What might be expected? Okay. All right, stacks. We talked about stacks a lot as well. Simple data structure. Some of these structures are very simple, and they're simple because, or we like them because they're simple. They allow us to do things fast in a lot of cases because of their simplicity. If the only thing you can do is pop off the top of a stack, well, then you only need to keep the top of the stack for your in your algorithm. It will, you can walk it back each time through. Right? If you and stacks solve certain problems that are hard to solve for other data structures, right? If you need to do something and have everything stored up and do it in a first in, last out situation, that's when you're going to use, or last in, first out, that's when you're going to use the stack. A few operations. We use it for a lot of things like tree traversal. That was a big stack-based thing. We did that on the lab. Okay. Here's a type of question we might ask. I'm seeing some people write this down. I could ask you to, I guess we could ask you to do a small stack, like write a little stack class, but probably not. You'll probably be more using it than writing it, I'm guessing. Okay. For sample questions, explain all the stack functions and how they're used. Like, what does it mean to do the top or pop or push? Like, what does it mean when you, you got to be kind of explicit about that. What happens with push? It's at the top of the stack. You put the value onto the top of the stack. Okay? Explain how to use a stack to do a post-order traversal. That would be kind of a long question, but you could say, okay, look, post-order means it's the following. It's going to be the you're going to have to say that it means that you print the node after you look through all the children, etc. Okay, and then how would we do that with a stack? We might have you draw some pictures. Okay. All right. Queues. Same thing. Queues are very similar to stacks, except now it's not last in, first out. I got that wrong. It is first in, first out, or last in, last out. Right. Insert at the end, remove from the front. Right, just like a regular human queue. Don't forget that. Okay, we have different operations that are very similar. In fact, remember during that lab, there is I think it was still, you used pop and top instead of DQ, but we'll call them DQ in here. I don't know, if you wanted to call it pop, I wouldn't be upset. If I just said, what's the difference between a pop on a stack and a pop on a queue? Well, it's the order of where the front of or the top of the queue or stack are. We did do a whole lab on circular queues. You might have to explain how a circular queue works. What are the disadvantages to, what are the advantages to a circular queue, right? What are the disadvantages? It's kind of hard to actually get the logic right to expand a circular queue if you have to expand it. Most of the time we don't have to expand circular queues. That's the idea, that most of the time you have lots of elements going in and lots coming out, so the queue size itself stays small, right? Sorry, I know people are still writing this stuff, but remember, this stuff is printable. Although if you print it, it ends up with these big black bars at the bottom, which is not good. Wastes lots of ink. All right, so write the in-queue function for a circular queue. Okay? I would not make you write the whole expand part, but you'd have to write the insert. You might have to write the in-queue function and talk about, hey, when the front of the queue gets to the last element, gets to the capacity, you have to rotate it around. You'd have to say if the capacity equals the, or if you'd have to, yeah, if the capacity equals the count of the queue, do the expand. I wouldn't make you write the expand, let's say. I wouldn't make you do too much in that case. But you might have to do some of that. Okay. All right, let's see, what else did we do? Trees. Lots of stuff on trees, right? Trees, nodes that have children. You should know some of the vocab, right? I mean, you should, if I ask you, what's the height of this tree, you should be able to tell me, and you shouldn't be going, oh, I don't know what the height is, right? That might be something you want to put down on your study sheet, is just kind of the vocab pointing to various points of a tree. Okay, siblings, leaves, path, length, all that kind of stuff. Remember, we could have trees that have links to all their children. In some cases, we do. This is sometimes hard to code if you don't say how many children are the maximum number of children. That's actually very difficult to code because you can't specify the number up front. Harder to do. You could have a linked list or something. Remember, we showed the directory structure. Uses a kind of a special weird one where we have like the first child and then the next sibling. Right? 2 pointers, first child, next sibling. That one gets a little ugly. It's asymmetric, which is not particularly fun when you're dealing with structures like trees. Sometimes it's necessary. Okay. Trees are good for recursive coding, right? Especially the binary ones. If you want to write tree functions, you can do them recursively many times. AVL trees, difficult to get that right if you're trying to do the rotate, but you can do that for trees. Okay. All right. Questions on that? I've got a couple more stuff on trees as well. There's binary trees and binary search trees. Remember that binary trees just have 2 children, and that was good because then we can say, hey, your node is just the data left and right pointers, and that's it. Right? We said that binary trees, the straight up binary trees, no pun intended, can degrade into linked list behavior. Why? Because you end up, if you insert into a binary tree that doesn't have a special property, like it must be, like it must be balanced or something, then you can end up with linked structures that go 4, 5, 6, 7, right? In fact, for binary trees that don't have any kind of structure to them at all, you can get terrible behavior, but you generally want some sort of structure. Okay. We talked about all the different ways we can traverse a tree: in order, pre-order, post-order, level order. I probably will not ask you to do a whole level order traversal queue-based thing. We did that in the lab. I'm not going to take the time on the exam to make you do all that, but you should know. I should be able to say, what's a level order traversal of a tree look like? And you say, oh, it takes the nodes in order from on the how deep they are, and it prints them out kind of this way, right? And what kind of search would that be? If you're going to print those out, if you're going to search that way, it would be called a breadth first search versus a depth first search. Questions like that. Okay. All right. Binary search trees. So we have this binary search. This is a big invariant here, right? We said that binary search trees have their left, all the nodes to the left are smaller, all the nodes to the right are larger, right? We said the average depth of a binary search tree is log n. That means that lots of our functions will be log n in their big O notation. Not all of them, but many of them will be, right? And that's a good thing because we like that. We'll get to asymptotic behavior in a minute or two. You need to know what we're talking about when we do find min, find max, contains, insert, and remove. And remember, remove's the harder one. I would study how remove works. Okay? I mean, study how remove works because you've got to remember the key to, there are a couple keys to doing remove, right? There's a bunch of there's 3 different cases, right? If it has no children, it's easy. If it has 1 child, it's relatively easy. If it has 2 children, you got to think about it a little bit more. Think about the asymptotic behavior of removing from a binary search tree. Okay. I might ask you to talk about lazy deletion. Like, why would we do what is lazy deletion, first of all? Remember what lazy deletion was? What is it? Yeah, you keep all the pointers in the same place, and you just mark it somehow, and you get to decide what that somehow means. You mark it as being deleted, and then you skip it in any of your cases. Well, that adds a little overhead, but it also means you don't have to do these weird remove things that might take some time. And if you've got special cases where you're talking about where you're inserting or you're inserting and you're removing a lot of items from a tree, and you know that you might delete it in one go through, and then the next time through you're going to restore it. Well, then why bother going through this whole thing of deleting it? Okay, so there's lazy deletion. So you got to know about those sorts of things. It is kind of amazing how much stuff we actually talk about in here, right? A lot of little stuff. Okay, so here's a type of question: describe how to insert or delete from a binary search tree. Okay, and I might say you would have to describe it. I might ask you to code it. I might ask you to draw it. I might say, look, draw the steps necessary to insert into this binary search tree, right? And you're going to say, OK, we walk down, we can do the comparison. We walk down until we find where it fits, and we find a null node and whatever. Explaining is a big part of this. Okay, coding up is part of it too, but I'm just as happy for you to say, I know how to actually describe it, because that's a much more abstract concept. Okay. Any questions on binary search trees? What kinds of questions I might ask? Okay, you guys are making it easy today. All right, then we did talk about AVL trees. We had some benefits to AVL trees, right? AVL trees was that compromise between a binary search tree that could go on in one direction forever and a perfectly balanced binary search tree, which is hard to implement because you have to, if you want to make all the levels exactly the same height, it's impossible if it's not a complete tree, but it's also tricky it takes too much time to actually make that happen. AVL is a good balance. I told you the dirty little secret about AVL trees, that they're actually not used in practice too much because there are other better rotation-based tree structures that actually work a little better in practice. But this one's not a bad one to look at because it shows you how rotations work. Okay, and there's an invariant here which says each subtree can't have a difference in height of more than 1 for every node. All of your subtrees have to have a difference in height of 1 or less, or 1 or 0. Questions on AVL trees? I won't ask you to program an AVL tree. Like I won't say, here, draw, write out the algorithm for this. But I might have you draw it, or I might have you explain how to do a removal or a double removal or something like that. Okay. All right. Remember all those weird cases we had? There's really only, question.
Do you have to worry about post order? We kind of glanced over that in lab. I remember being.
That's right. We did glance over post order. Yeah. You should be able to describe it. I mean, if you need, if you don't understand it, what you should probably be able to do is say, here's a tree. And the lab's a good example of one. Take the hand up in the lab and say, how do I write all these in their orders? And just kind of walk through it, and you can test it because you wrote the code for it. So you can actually test it, except for the post order. But post order, I think it describes the algorithm a little bit. But you can certainly look that up. And we think we talked about it a couple times in class. Yeah, you should know it, but I probably wouldn't expect you to code it. Maybe, but I doubt it. Yeah. If that means anything. What does that mean? Oh, OK. All right. So AVL trees, draw rotations. They're coded with recursion in most cases. Why? Because actually it's easier to do than the non-recursive case. What's the downside to doing it recursively? Tends to be a little slower, right? And then AVL trees, hey, we get this great log n for all operations. Even during the rotation, that only adds a certain number of constant steps to doing the rotation. Okay. All right. Let's see. Explain how to insert into an AVL tree. Like, what do you do to insert? Well, first you go down and you insert into the tree like you would a binary search tree. Then you have to look at then you have to walk back up the tree. Remember what else we keep? What other thing is really important to keep at each node of a binary search or an AVL tree? Besides the pointers to the nodes, what else do we need to keep? Yeah, Ian? The depth. Yeah, we need to keep how high it is. Yeah, the height really of each node, so that the parent node can figure out, do my subtrees differ by more than one? Yeah, you need to do that. The recursive solutions to that are pretty good. Question, Zoe? Yeah, let me bring up the well, we can, trying to think of the easiest way to do that. To draw the rotation. Yes, let me go back and bring up the other slideshows because it's easier than making up nodes that don't necessarily make sense in that case. So let's see. Balanced trees, I believe it was. Here it is. OK, so let's look at a single rotation. OK, here we go. A single rotation. Remember, what you do is you look and you say, for each node, you say how much do they differ by. K1 differs by 1. We don't care about, like, K1 is OK. OK. K2, this one has a height of, I guess a depth of 1. This has a depth 1, 2, 3. So that's not good. So this is the one we have to do. What do? You go in the direction of the one that's bigger. You grab the next node down for a single rotation, and you shake it, right? And that becomes the top node, right? And then you say, OK, if this one's now the root, rather the root node, if K1 is now the root node, all right, what does that mean? You have to do a little bit of logic. You have to say, OK, that means that everything on the x side is still going to be less than K1. That's fine. Well, y is going to be bigger than K1, so it needs to fit on the right-hand side of K1 still, like it does over here, x side and y side. But K2 has got to be bigger than y, so y has to be on the other side of K1. You just have to figure out the details. Again, I'm not making you code this. I'm just going to make you possibly draw it, for instance, or explain it. Yeah?
So in terms of you're actually drawing it, you just have to show kind of the previous tree and the new tree?
Yeah, that's what I would do. I would pretty much have you do the previous tree, new tree, and then maybe the steps to do it. Like if it was for the insert, I'd say, how do you do the insert? Oh, you'd say, first you walk down this way, and you'd draw arrows walking down. And then you'd maybe label them with numbers, say what the order is. Then you'd say, oh, now I have to rotate. Oh, it's going to be a single rotation, et cetera. Yeah. So that's the level of detail there. Not going to make you code it recursively or anything like that. Okay. Other questions on this one? You should know how to do the double rotation as well. And just know kind of what that looks like as well, like when you need to do that. Right and left of a subtree, etc. Okay. All right. Let's see. Go back to here. Other questions on AVL trees? Okay. All right. So remember we briefly talked about this. You can represent trees as arrays, right? And how do you do that? Well, first of all, you generally need a complete binary tree unless you want to mark which positions are empty, which you can do. And then we've got a couple formulas here. These are the kinds of things you probably don't need to necessarily memorize them, right? Write those things down on your sheet if you're gonna say, oh my gosh, I don't remember what all the where's the right child? 2i plus 2. Oh my, I do have to remember that. No, you write that down, right? But you need to be able to explain maybe why this is, what's going on here. We don't need any pointers for this. Trees without pointers, amazing, right? The pointer is built in to the idea or to the math of these formulas. You do a bit of math, a bit of arithmetic, and you figure out where the next child is based on that arithmetic. It's very fast and it's efficient, and you don't need to, and you've still got this nice array structure. Kind of a cool idea. Okay? We can do non-complete trees, but we need a way to designate whether their cells are empty. And of course, non-complete trees, you've got this trade-off. Remember, if you're doing a binary search tree and it's not balanced, it might end up in that degraded linked list form. Well, you're still going to end up with a really long depending on how deep it is, you could end up with a really long array that you need to store this in, and it won't have any values in it. That's the trade-off. Okay. Questions on that? Okay. All right. We also did talk a bunch about asymptotic or big O notation. Remember, this is how you fundamentally do those comparisons. Okay. How do we do those comparisons? Well, you should be able to read through the code and say, this is a little like one-off statement. Call it one or two primitive operations, right? I'm not going to take any points off if you called it 1 and I thought it was 2 in general, right? I will take off points if you forget that a loop is going to go through the array or whatever loop it is n times, and that's going to be order n. Like those are the big things you need to know about. You need to be able to pick out that sort of structure out of these things. We always disregard constants, right? The only time we would ever care about a constant is if we had a huge constant that kind of overwhelmed the fact that we were doing n number of objects, right? I mean, if you were counting objects and all of a sudden every time you had to multiply by 10 to the 10 or 10 to the million or something like that, yeah, then you wouldn't ignore it. But I will not ask you cases about that in general. Okay? You should be able to talk about any of the functions or any of the data structures we've discussed in terms of their big O notation. If you can't, if you don't know off the top of your head, you should be able to reason through why it might be big, a certain big O notation. Okay, and you should be able to discuss the differences between some of those types of operations. The one that I'm not really going to ask you on, although you'll probably get it later in the term, maybe in the final, is n log n. Generally, don't worry too much about n log n. The other ones we will worry about, right? Holy Grail, constant. We've got logarithmic. A lot of tree operations are logarithmic, right? Linear operations, quadratic, and other polynomials, right? This gets into the bad news. What did I say a big use for quadratic equations were, or quadratic type behavior is when you're doing what? Nested loops. And what's a kind of a big case that you guys that we see a lot in computing? What is it? GPUs, yeah, because they use graphics, and graphics are two-dimensional, right? And so you're generally going to have, looping through in 2 different dimensions. If you're going to have to loop through in 3 different dimensions for like 3D stuff, well, now you've got polynomial cubic type behavior, and that's even harder to deal with because it takes more time, and it's not a efficient type of algorithm. And then I won't make you actually just obviously write out anything that's exponential, but just know that that's bad news. If you get exponential types of functions, you're not going to be happy. Okay. All right. Let's see. Did I put this one in here? Yeah. So here's some hints. Right. Order 1, not dependent on the number of objects in whatever data structure. That's great. If you can do things in order 1, we like that. Right. It's going to be very fast, no matter what kind of structure. It means it really means that things can scale very well. Meaning that you can add lots and lots of objects, and you end up not hurting your performance. Okay? Not possible in all cases. In fact, in many cases, but in some cases, you can get order 1 behavior. And if you have to access every element or a significant portion of them, then it's going to be order n behavior. Sometimes you can have a best case, which is order 1 behavior, and a worst case, which is order n behavior. Right? If you're searching through, if you're doing a linear search, remember, a linear search goes boom, 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 through all the ones. If you're searching for a particular value, it could be the first one. Your best case is it's the first one and you find it. Awesome. Right? Well, it could also be the last one, in which case your worst case is order n. And we generally care more about worst cases than best cases because that's the one that's going to kill us if we have lots of the worst cases. Okay? And let's see. Nested loops for n squared, doubly nested loops for n cubed generally. Be careful with that, though. Make sure that it does have to go through all n elements in a nested fashion. And then log n. If you're breaking the problem into halves, you're generally going, and each time through you only have to do half as much stuff. Well, that's a logarithmic behavior. In fact, it's log base 2. If you can split things into three things, then you've got log base 3, which is even better. Not always possible in a lot of cases. Okay. Questions on big O notation? Awesome. All right. Well, the sample questions are kind of like big O notation. I'll probably ask you some particular questions about it. But, oh, sorry, you had a question.
Yeah, for the recursion, like the sum is that order n?
Let's think about this. Is this order n? So if n is 0, 1, if n is 3, how many times do we have to recurse through here? Yeah, n times. So yeah, that's an order n behavior. Now, it gets a little more subtle when you think about the constants, but I'm not going to ask you those. But yeah, this recursive ones are sometimes difficult to analyze. But if you can say, look, I'm not breaking this I'm not breaking this down into halves each time or whatever, right? Then you could, you would say, yeah, that's order n. Good question. Okay. So order n behavior is kind of, you got to kind of, I can sprinkle it through a lot of the different parts of the test. I may ask some specific questions that are based on that, but I could also, in any question, say, describe the big O notation for this algorithm, or for what's the best case and worst case, and so forth. I will not ask you average cases that you have to figure out. Okay, the only average case you could probably really worry about is, binary search trees have an average depth of order log n, that sort of thing. Okay, but I won't ask you details about the average cases. All right, you'll get that in algorithms class. Okay. Then we talked a little bit about prefix trees, right? This is another way of thinking about a tree-like structure. This is the hey, you got a dictionary here and lots of prefixes are shared. Well, let's put it into a form that can compress that a little bit, right? We get some great behavior out of it because it's based on the word length, not the actual number of words. It says, I don't care how many elements are in my try. I can actually I can do a search for a particular word. Only like the big O notation is based on the number of letters in the word, not the number of words in the dictionary. Awesome. Okay. Turns out Yoda's not a fan of tries. Let's see. And if you didn't come to that lecture, you're like, what? What's he talking about? All right. Let's see. What else? Tries. Do I have another slide on tries? Yeah. So remember with tries, we have to mark where words end with tries, right? Because as you're walking through, you need to know, hey, did I make it to a word or not? Right? Even though, let's see. Even though, what's a good example? I don't know, da could be a word, right? Well, if it's not in our dictionary, then when we get down to DA and we're searching for DA, we would say that we do not find it. Even though DA is in there, we would not find it because it's not a word that we've input into our dictionary. Okay? If we're searching for the letter P or something, same thing. We've got a P in there, but if it doesn't have an asterisk or say that it is actually the end of a word, it is not the end of a word. Okay? And you can go online. I fixed up the try animation thing, so it works a lot better than it did when I showed you in class. So you can play around with that. It's online. Okay? Yeah, question. How would you describe a try?
I don't know, it's like a DST, but it has like a specific number of like children.
Yeah, it's similar to a binary search tree, although it's definitely not a binary tree, right? Because you've got lots and lots up to a certain maximum number of children, which is not binary, right? So, but we do generally sort each individual letter in a ordered fashion. So yeah. The only common use of it? Well, I would say, I would not want to limit myself to the only common use, but common uses are for dictionaries in languages that happen to have lots of similar prefixes. I mean, that's a good use for it, and you've probably, your phone probably has a try built into somewhere there that because of the fact that you use dictionaries for all that. Your spell checker or whatever probably has a try built in somehow as a data structure. Other questions on tries? Yeah?
So
Yeah, that's a good question. It depends on how you set it up. But yeah, the C here could have 25 either null pointers or pointers that are empty, and however we define empty, right? Could be a null pointer, it could be some other way of doing that. Yeah, that is a downside to this. If you're going to do this method, each individual letter is going to have lots and lots of children. And so that's going to be where the compression kind of fails you in that case. Now, you could do it such that C has a linked list, and you kind of will keep the linked list ordered in some fashion or another. And then you don't need all those extra pointers until you build it in. And in fact, for a sparse tree like this, yeah, you might just say, nope, we're not going to keep those around. We're going to take a little bit of performance hit for each letter going down, but it's going to, in the end, it's going to be a better idea. Yeah. Good. Okay. All right. We can also compress them. I won't. I probably will not ask you about how to do compressions and so forth. Although somebody was telling me, one of the TAs was telling me that she had an interview, and she had never heard of a trie, but she hadn't gotten that far in data structures, I guess. But they asked her exactly this. They said, "So you have a compressed trie like this. How would you actually insert into it?" And she said she figured it out. I mean, she said, "So what do you mean by try?" Right? And then they said, "Oh, well, OK." And they explained it a little bit. And she said, "Oh, I see. OK, I get what it is. You go down and you, like she said, how would you insert, I don't know, like find into this? OK, well, you go down here and you say fi, and then you'd say, oh, you go this way because it's less than the, it's the less than the middle or whatever, and you put it." So she worked it out, but she had to draw it on the board. They didn't say code it. They said, here, draw it on the board, right? Yeah.
What are the 2 pointers for pit 22? Are those characters?
These little guys? That means that that means that there are 2 words there. Pit is a word and pits is a word.
They are pointers for nodes.
Those aren't pointers. Those are just, in this case, they're just asterisks that say, hey, this is a word. That's all that means in this case. Let's see, on the online animation, I actually made it colorful instead of, I think I might also have the asterisk, but that's all it means. It's not a pointer in this case. Yeah. Sorry for the confusion. OK. All right. Let's see. Here's a sample trie question. Why is a trie called a prefix tree? Like, what's the point? Like, why is it also called a prefix tree? What's the prefix part of it? Like, what's that all about? And you can say, oh, because nodes share prefixes, or words share prefixes, and that's how the compression happens. Okay. All right. Let's see. Then finally, we talked about priority queues. This was like last week, right? So we talked a little bit about priority queues, and it's based on this idea of you have a key that lists the priority for a node, or for an element of some sort. Keys don't have to be unique. We've got those. We have to have an order. We have to be able to order them, right? Duplicates, you can't, like duplicate keys, you cannot order. You don't get to decide which, if you ask for something with a particular key, either you get all of the responses, like you could build your priority queue such that you'd have to extract all of the minimum ones, or you would get only one and you don't get to decide which one. If you needed to have a priority difference between 2 elements, make them different priorities. Okay. Keys are actually stored with the elements. This is the first key-based structure we look at. We will look at many others. Okay. And we have a number of operations, much like stacks and queues. They're easy, and they're easy such that they make things, they make things good for us, right? We actually have insert item, min element, and remove min. And by the way, Chad M, are you here, Chad? Chad M? Yeah, Chad emailed me and had a really good question about removing and how to make it the asymptotic behavior better than order n. And it was a very good question. And then I went back and looked, and my code was completely wrong. My code was actually order n squared, and I'll show you how to fix that. So thank you for pointing that out. We had an interesting discussion online on the email about that. Well, it's basically me saying, yeah, you're kind of right. I was wrong on this. So that was the discussion. So thanks, Chad. The 3 big, you should know what it means to do insert item, min element, and remove min from a priority queue. And by the way, we did it in 2 different ways, remember? We said we did it in an ordered sequence where you had to do the ordering when you put it in, and that gave us one behavior. And then you had the unordered, which gave us a different behavior. So in the unordered case, this is what I said. Oh, sorry, it's a little dark here. this is what I originally said. Remember that I wrote this little helper function that just finds the index of the value that's the minimum. And how does the helper function work? It goes through all the elements and returns the index for the one that happens to be the minimum key. Okay, so it must go through all the elements because it could be the last one that's the minimum, so you have to go through all of them. Okay, and that was definitely order n behavior. And then I had this in here, and I said, oh, okay, let's say we're going to go through the we're going to walk back. We're going to walk starting at the minimum index and then all the way to the end. And we're going to actually move the items back one. We're going to delete an item by moving everybody back one, right? Well, I think I mentioned during the lecture that was only order 1. It didn't really matter. It's not, is it? What if the minimum value happens to be the first one, right? Then you have to move all of them, right? So you'd have order n behavior here, and then you'd have another order n here. So what's the total asymptotic behavior of this? It's what? Not 2n, n squared, right? Which is ugly, right? And we don't like that. So bad news, Chris. Don't program like this, all right?
Squared, why isn't it just twice of the n?
Oh.
Because it's not like they're nested or anything like that.
They are not. Let's see.
N just happens.
Oh, you're right. Well, wait a minute. It is 2n. You're right. It is 2n. Yeah, I guess you're right. Yeah, because they're not nested. That's a good point. For each element, you don't have to then go through the whole list. You are absolutely right. So it is 2n. So I guess you're right. In this case, it's still order n behavior, but it's not the best we can do. That's, I guess, where I should leave it. Any ideas on how I could make this better? I will give you a hint. You don't need to you don't need to keep the order of any part of this structure. Am I keeping the order by moving everybody back one? I actually am, right? I've said that if this is where, do it this way. Whoops. All right. So if, right, I was removing this one, right, and I move everybody back like this, okay, I have to go through that whole list again. That's another n behavior. That's another n times through on worst case, right? If these are all still in order, but in an unordered list, I do not need to keep them in order, right? So in that case, can anybody think of what I would do instead of worrying about moving everybody? Yeah. Yeah, just move the last one down there, right? Don't worry about moving all the other ones. Just move the last one in there. Then we've still got an unordered list. We've still got all the elements. And the last one is just an empty one now. We make our count go back down by 1. So yeah, so we like that, much better. Okay, yeah. So anyway, sorry for making it seem like there was more to it than that.
Why is that PQ size -2?
Let's see.
Size -1.
So yeah, let's see. Should it be -1 or -2? You haven't decremented yet. It probably should be 1.
No, but is it PQ size
PQ size is.
empty spot?
Hold on. So this is the next empty spot, right? That's PQ size, right? And so we want to move the last one down. So yeah, it is 1. Yeah. So I did it wrong again. Great. Wonderful. All right. Whoops. Hang on. No, I can't even do it in there. Hang on. Not letting me. I'll have to do it. I'll have to do it some other time. Oh, it's probably because of this thing. Hold on. It's because of the fact that I can't grab the. There it is. And then this one. There we go. Questions on that? Looks better. OK. All right. So we talked about this. We said we can order priority queues. We can have ordered ones or unordered ones. We've got these trade-offs. You should be able to talk about the trade-offs and why we care about the trade-offs. Like, what case would we use an unordered versus an ordered priority queue? Okay. Let's see. Do I have any sample questions on this? Yes, I do. Explain the function, explain the trade-offs. There you go. Okay. And believe it or not, that's actually everything we covered up to the midterm. OK, I've got about 5 more minutes. Other questions on types of things we could have in the midterm? Anything else? I think I've gone over a bunch of types of questions you can look at and try to do on your own. The odds are that I won't ask any of those particularly. But you should think about, hey, OK, if I could do this, what else can I do now? You know, questions like that. Yeah, Ben.
Something like a queue, will you give us the header file and
Yeah, for something like a queue, if you have to do code, you will have enough information about the details, like variable types and the class type and all that. You'll have enough details to be able to write it. You won't have to, or if you don't, look, if I goof and you don't have enough information, you'll have to say in there, I'm going to define this to be the index for whatever, or the thing. So, OK. All right. Other questions? Yeah.
What do you think the most amount of code you guys write?
The most amount of code, 7 or 8 lines in a row. I mean, not more than that. It's not going to be a whole page of code. Okay. Some midterms in the past have been that way, and I don't think that's the best way to use our time for a test like this. Yes, Trent?
You have lab today.
We do have lab today. Yep, it's going to be more debugging, but this time using a debugger, okay, which is good. Other questions? All right, I'll see you guys at lab or on Wednesday.